Welcome back, boys and girls, ladies and gentlemen. We are looking at Chapter 4, Section 4 today, which is proving triangle congruence. Now, in our last video, we looked at what it meant to be congruent. And if we had two triangles, for example, like so, we've got triangle A, B, C, and then say W, X, and Y. We showed that we had to have all three sides that correspond there, obviously, all three sides being congruent, as well as all of those corresponding angles to be congruent. And that's all well and good, but today we're going to take kind of a different approach. We're going to look at what if we only know a portion of each triangle. So we've talked about how or what it takes for triangles to be congruent. We're going to look at ways to prove whether or not they are, and it comes to find out we only need a limited amount of information. We don't need all three sides. We don't need all three angles. We only need a little bit. So let's take a look at it. The first idea that we're going to look at is this one called the side-side-side congruence postulate. We will simply refer to it as SSS. Okay? Pen's out of ink. Let's try something else. There we go. So we're going to refer to it simply as SSS, and it's talking about congruence. Take a look. Here's what the postulate says. If the sides of one triangle are congruent to three sides of a second, then the triangles are congruent. So in other words, if I've got triangle ABC, and those three sides, AB, BC, and AC, are congruent to the three sides of another triangle, then automatically we know that it's congruent. Okay? So that's what the postulate states. So long as, for example, AB in this case matches up with DE, and if BC matches up with EF, and then, of course, our last side here, if AC matches up with DF, then cool, we can say triangle ABC is congruent to DEF. So long as we can prove all three sides are congruent, then wonderful, we have congruent triangles. So we could, for lack of a better word, ignore the angles in that case. But once we've proved the triangle congruent, so say, for example, what if we had to take this situation a step further? What if we had to prove, for example, that angles C and F were congruent? Well, then one thing I could do is prove all three sides match up. And now that I know sides, I can use C, P, C, T, C, corresponding parts of congruent triangles are congruent. Once I know that all three sides are congruent, thus proving the triangle's congruent, that means, for example, C and F have to be congruent by the CP-CTC statement there. Corresponding parts of congruent triangles must be congruent. Awesome. So let's see if we can use this in a proof. You knew proof was coming. So take a look. Here's a nice, neat, short proof. So in this case, we were told that segment GH, so this segment here, we'll mark it, is congruent to KJ, so this segment here. We also know that HL, this segment here, is congruent to JL, this segment here. And the last piece of information we're given about this diagram is that L is the midpoint. So L is the midpoint of GK. We're trying to prove that our two triangles are indeed congruent. So let's get started. The first statement I'm going to make is all that given information. We're just going to go ahead and throw it all out there, and our reason is given. Now notice we know that two sides match up, two sets of sides. We've got to get the third. And notice in this case, we're told that L is the midpoint. Remember, we're trying to prove congruence, not equality. So I do not want to say, or I could, I suppose, say that GL is equal to LK. And we could say that by the definition of what it means to be a midpoint, but then we would have to take an additional step to make congruence. I think there's a better way. Let's say in this case that GL, and we'll say segment GL, is congruent to segment KL. And let's think about our reason. We can't use the definition of a midpoint because the definition of a midpoint implies equality. In this case, I'm going to use the midpoint theorem. And remember, the midpoint theorem states that what we've got here is indeed a congruence issue. So I can show that these two sides are indeed the same. Now that I know that, I can get into my proof statement. So triangle GHL is indeed congruent to triangle KJL. And we can say that by the side congruence postulate. And again, we'll just reference it as SSS. SS. All right. Well, let's talk about one more. There is one other way that we can show our triangles are congruent without having to know absolutely everything. And that's this idea. We call it the side angle side congruence postulate. And again, we'll just abbreviate it by side angle side, or SAS. Here's what it states. If two triangles and the included angle, now notice how this is done up. I've got side AB, I've got side BC, and the included angle is angle B. Notice it's included because it's between those two angles. What we can't have is, for example, AB, BC, and then talk about angle C. That would be a side-side angle situation, and we don't want to write that out. So, and if you're not sure what I mean, try writing it the other direction. So no side-side angles here. We need side angle side. So again, if two sides of the included angle of one triangle are congruent to the two sides and included angle of a second, then the triangles are congruent. So in this case, if I know that AB and DE match up, and that angles B and E match up, and last but not least, that BC, there we are, and EF match up, then that's enough to prove the triangle's congruent. So long as I have a side, an included angle, and side for two triangles, then that's enough for me to prove, hooray, hurrah, they are congruent, and that's all we need. So let's try another proof. If I can get the page to turn. Here we go. So take a look. In this case, we've got a diagram. It looks like a lighting situation, maybe for a stage or whatnot. So it says the scaffolding for a stage lighting shown appears to be made up of congruent triangles. So here are these triangles. They appear to be congruent. If segment WZ, so there's this here, is congruent to YX. So let's go ahead and mark them. WZ, that's here, and YX, that's here. So we know that those are congruent. And notice we're also told that WX, so let's kind of make this bold here, that this segment, of course we could extend it if we need to, this segment, we'll put an arrow in there, is parallel to ZY. So let's kind of darken that in. So these two lines, we'll go ahead and extend them, are parallel. Write a two-column proof to show that WXZ, so this triangle here, is indeed congruent to triangle YZX. So we've got, we'll number the triangles here. We got this triangle here, and then the second triangle here. All right. So I've gone ahead and given you all of the statements, and gone ahead and shoot, I even gave you two of the reasons. And in this case, you don't have to put these two statements separate. In this case, we did just to make it a little clearer. But we've got our congruent sides. We've marked those. We've got our parallel lines there. So we got those marked, all given. Let's look at this next step. WXZ, so let's find that. WXZ, so this angle here, we're told is congruent to angle XZY. So this angle here. How in the world can we make that statement? So there they are, I've marked them. How can we make that statement? Well, again, if we've got parallel lines, and this is a transversal here from Z to X, well, that means these are alternate interior angles. So we can say that those are congruent by the alternate interior angles theorem. Cool. So notice we have a side, we have an angle. Now we need a little bit more, right? We need a little bit more to make this work. So take a look. This next one is XZ. So XZ, so this here, is congruent to ZX. So notice, one's going one direction, one's going the other. So let's mark it. And we can say that based on the, what can we say if the order is slightly off? In this case, it would be the symmetric property of congruence. Now, some might say, well, wouldn't that just be the reflexive? It's the same thing. Well, notice we're going in a different order. If we said that XZ is congruent to XZ, well, then I'd be all for it. In this case, we've got a slight order difference, so symmetric property would be the way to go. So let's look at our two triangles here. I've got a side, but then the angle's over here. That's odd. We've got a side, and then the angle's over here. Huh. We said that we're looking for side, angle, side. What we've got here is side, angle, side, angle. Okay. I like showing people this proof for one reason. A lot of people would look at what we've got. Oh, I've got sides, I've got an angle, cool, side, angle, side, and say that they're done. But notice what we've got here. We've got W, Z, Y, X, cool, we marked them. We then have our angles W, X, Z, so right here, and then X, Z, Y, right here. And then the angle, or excuse me, the side that we're including there is this one. Well, let's look at triangle 1, side, angle. Look at triangle 2, side, angle. So as a matter of fact, this proof is invalid. And again, I show this proof for this reason. A lot of people look for 2 sides and an angle and think that's enough. No, 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 no. Let's redraw this. Draw it down here. And let's see if we can't do better. So we've got W, Z, X, and Y. If I can draw, there we go. We know that these are the same. These are the same. And then finally, of course, that this shared side is the same. So notice side, angle. What would we really want in this case so that we could use side, angle, side? Because again, this proof, it's invalid. We can't use it. Okay, what would we need here? Well, we could use a couple of things, right? It would be better if we could show, and I'm going to mark this angle here and this angle here. And then let's get rid of the one they gave us. If that's what we had been able to work out, then notice that would work for side, angle, side. We've got side, included angle, side. Side, included angle, side. That would work. But what we actually have, okay, based on the problem, is this. This is actually a side, angle situation, and we can't prove that, okay? We would need more, okay? And at this point, we don't have enough information, so be careful. So again, let's recap. The 2 ways we can prove at this point, we've got congruence issues. We can use our side, okay, if we want a shortcut. We could also use side, angle, side, if you'd like. And then, of course, you've got the old standby where you have to look at all sides and all angles. Of course, let's be clear. If you can find all sides, well, guess what? You've already done that. Here's what you can't do, though, and we'll talk about this in another video. You cannot simply say that if all angles are the same that we've got congruent triangles. That doesn't work. Okay, we'll talk about that a little later in another chapter, but this won't fly. All right, so if we're talking about true congruence, I can't just say, oh, all 3 angles, that works. Nope, it doesn't. All right, make sure you take good notes. If you've got questions, bring them with you. But be careful, folks, that we don't end up writing invalid proofs or going down a line of logic that doesn't work. We're looking for side, angle, side, or side, side. None of this SSA business. All right, have a good day. We'll see you in class.